This is amazing. Look how fine it works. I can play with this whole day. When an object moves in your room, it changes illumination level a little bit in environment, and it is enough for us to detect that movement. In this video, I'm gonna teach you how to make a circuit to detect that tiny changes. Actually, we are going to make a motion detector. But in this video, I'm gonna use basic components, and after watching this video, you will fully understand what is going on inside a motion detector and how exactly it works. It works based on illumination change in environment. When an object moves in front of the sensor, the amount of light sensed by the sensor changes, and this is most basic point used in the circuit. In this video, I will explain the circuit in detail and show you how exactly it works. After watching this video, you will understand what exactly do every single component in the circuit. This video will improve your understanding of analog circuits. Please stay with me in the rest of this video. Everything starts from this cute component. It is called by different names: LDR, photocell, photoresistor, etc. Photocells are available in different specifications. Three main characteristics of photocells are shape and size, light type they sense, and resistance range. Its job is to measure illumination level in environment. How it works, I'm gonna explain. This component is a kind of variable resistor. By changing illumination level, resistance between its terminals changes. Let's do a simple experiment. You see what happens when I increase illumination level, the resistance gets smaller, and when I decrease illumination level, resistance gets bigger. Now it is about 1.5 kilo ohms, and now it's about 0.6 kilo ohms, about 600 ohms. If I cover the sensor with my hand, it can get bigger even more. Now it's about 11 kilo ohms. You saw that an LDR changed its resistance when illumination level changed in environment. But what it has to do with our circuit? With a little knowledge about electronic circuits, you probably know that variable resistors are useless in electronic circuits by themselves, and we have to convert them to a variable voltage source. I mean, we have to make a circuit to convert a variable resistor to a variable voltage source. After that, we can use them in our circuit. This is a very simple voltage divider circuit. It consists of two resistors, R1 and R2. Voltage on this point, point A, is directly related to VSS and resistance value of R1 and R2. With this simple equation, we can calculate voltage on point A. Let's suppose VSS equal to 9 volts, R1 equal to 5 ohm, and R2 equal to 10 ohm. Then voltage on point A is going to be 6 volts. It is obvious, if you increase R2 value, voltage on point A will be bigger, and if you decrease R2 value, voltage on point A will be smaller. Then, if you put an LDR here instead of R1, voltage on point A will be directly related to environment illumination level. If you use an LDR here instead of R1, then by illumination increase, resistance value of R1 will get smaller, and eventually voltage on point A will get bigger. But if you use an LDR here instead of R2, by illumination increase, resistance value of R2 will get smaller, and eventually voltage on point A will get smaller. Let's set up this circuit and probe point A with oscilloscope. By hovering my hand over the LDR, voltage on point A changes. Till now, we have been able to measure illumination level change in environment and convert it to voltage level by using a simple voltage divider and replacing one of those resistors with an LDR. Good progress. Now we can make a simple photocell circuit which turns a light bulb on at night and turn it off at day. But it is not subject of this video. There are a lot of videos and circuit diagrams about photocells on internet. You can use them to learn how exactly a photocell works. In this video, we are going to make a circuit to detect sudden illumination change in environment which is caused by an object movement. It seems weird. In this diagram, we have point A, which shows us environment illumination level. What will happen if I add a point B here and add a resistor between point A and B, then connect B to ground using a capacitor? Let me explain. Let's assume that illumination level in environment is constant and nothing is moving near LDR. In this situation, voltage on point A will be stable and constant and it will show illumination level at that time. Capacitor on point B will charge to same voltage as point A. So voltage on both A and B will be equal. In this situation, if an object moves near LDR, it will change illumination level sensed by LDR and eventually it will change voltage on point A. But voltage on point B will reach to new voltage of point A gradually with delay, because capacitor is being charged through this resistor and it's a time-consuming process. If voltage on point A is different from voltage on point B, it indicates sudden illumination change in environment. Maybe something is moving in front of LDR. No matter which one is bigger, voltage on point A is bigger than voltage on point B, or voltage on point B is bigger than voltage on point A. In both cases, something is going on in front of LDR. If voltage on point A is bigger than voltage on point B, it means illumination level in environment suddenly increased. And if voltage on point A is smaller than voltage on point B, it indicates illumination level in environment suddenly decreased. Actually, we are using capacitors in this project to make delay, and this is key point of this video. We can use voltages on points A and B to detect movement. Let's set it up and probe points A and B with oscilloscope to better understand what is going on. The yellow signal shows voltage on point A and the blue signal shows voltage on point B. This experiment shows when my hand gets away from LDR, it allows more light to reach the LDR, and then voltage on point A get bigger than point B for a moment. For example, look here, in this area, blue signal is under yellow signal. And when I move my hand close to LDR, it blocks more light and it causes voltage on point A get smaller than point B for a moment. For example, here in this area, yellow signal is under blue signal. I'm a human operator and I'm using oscilloscope to detect these conditions. So what we can do? There is no oscilloscope and human operator on our circuit to continuously check voltages on points A and B. What we can do? There is a useful component named OpAmp. It can do this job for us. We can set up an OpAmp in comparator mode, then it can compare two voltages on two separate points of our circuit. There are a lot of OpAmp ICs available in market. For example, LM324 IC contains 4 OpAmps in it, and all of those OpAmps are in comparator mode by default. Comparator mode means if voltage on positive input of an OpAmp, for example terminal number 3, is bigger than its negative input, in this example terminal number 2, then its output terminal number 1 become active. And when voltage on positive input is smaller than its negative input, then output become inactive. If you connect terminal number 4 to 5 volt for example, and terminal number 11 to ground or 0 volt, then the IC start operating. After that we can connect points A and B here to inputs of OpAmp. There are 4 of them, no matter which one to use. You can either connect point A to positive input and point B to negative input, or point A to negative input and point B to positive input. Interesting point is here. If you connect point A to positive input and point B to negative input, then output of OpAmp will become active when illumination level in environment suddenly decreased. And if you connect point A to negative input and point B to positive input, then output of OpAmp will become active when illumination level in environment suddenly increased. In this project we will use 2 OpAmps to detect both of them, but for now I'm gonna test one of them. Let's set up this circuit and test it. Look at this LED. When illumination level is constant, output LED is blinking very fast. Maybe it is not observable in video, but it is clear when you look at it by your eyes. When illumination increase, it become completely off. Look here for a moment. It become completely off for a moment, and when illumination decrease, it turn on completely. Look here. This is not the thing I expected. I think there is a problem. Let's prop point A here and OpAmp output to see what is going on, to find the reason. Look here, this yellow signal is output voltage of our sensor here on point A. And this blue signal is output of OpAmp here on terminal number 7 of this IC. You can see the noise on yellow signal. Most of these noises are because of low quality output of the switching power supply. I'm gonna change this with my linear bench power supply to see the difference. Most of noises are gone, but there is still a tiny noise here on point A. Its amplitude is not much, but it is enough to ruin the output and force our output to blink like this and make these pulses. Let me explain what is going on here and where did these pulses come from. This signal is on point A here and this signal is on point B here. On point B, the sinusoidal part of the signal is filtered because of existence of this resistor here and this capacitor here. So here on point B, there is only DC part of the signal. When the sinusoidal on point A is in its negative half cycle, positive input of OpAmp become greater than its negative input, and then output become active and turn the LED on. But in positive half cycle, it turns the LED off. This is why these pulses appear on OpAmp's output and you can see them on oscilloscope. You may ask, where are these noises come from? This is a good question and I'm gonna answer. There are three different suspects here. First suspect is the LDR itself. Maybe this noise is produced by the LDR itself, but I think it is not considerable because LDR is a passive component and it is less likely. Second suspect is the power supply. Maybe this noise is coming from power supply. We can simply test it and check it out. I'm gonna prop power supply with channel 2 of this oscilloscope and see if there is a noise on it with same frequency. There are ripples on power supply, but these ripples are not source of this noise. But this noise is somehow the source of these ripples. These ripples are here because of this LED. When this noise makes this LED turn on or off, the LED draw a little current and it's cause voltage to drop a little. If you remove this LED, you can see those ripples on power supply are gone. Look here, there are noises on power supply, but frequency of the noise on power supply is not same as the frequency of noise on sensor output. Also, amplitude of the noise on power supply is not comparable to amplitude of the noise on sensor output. So the power supply is innocent. Third suspect is the environment itself. Maybe this noise exists in the environment. I mean, maybe the light in my room have this noise in it. I don't have instruments to analyze the light in my room, but I can test it using other methods. Maybe a super smart method. I am using CFL bulbs in my room. I think these bulbs can produce such a noise in environment illumination. I can simply turn the bulb off and see what will happen. Yes, we found the criminal. Congratulations, we found the criminal. This guy ruined our circuit, but it is not enough to find the criminal. What we can do now? How to deal with this noise? We can use RLC filters to reduce this noise, but in this case I have a better idea. We can shift the voltage or bias the voltage. I have already said that if voltage on positive input of an OpAmp is more than its negative input, then its output will become active. In normal situation, DC voltage on points A and B are equal. But voltage on point A have additional tiny sinusoidal noise with amplitude around 20 millivolts. Look here, volt diff is 10 millivolts and then amplitude of this noise will be something around 20 millivolts. What if we add a tiny DC voltage to negative input? This is point A. This is the signal on point A connected to negative input, and this is the voltage on point B connected to positive input. What if we add a tiny DC voltage to negative input, this one? This one will go up a little and it probably solve our problem. If we add, for example, 50 millivolts to negative input, this one, in normal situation, output of OpAmp will be inactive and do not produce pulses like this. Because how negative input, considering sinusoidal noise, will be more than positive input. Also, we can subtract a tiny amount of voltage from positive input to solve this problem. You may ask how to do it. how to add a tiny voltage to this one or subtract the tiny voltage from this. I'm gonna explain. This is point C. Voltage on point C in this diagram is always equal to voltage on point A. Instead of connecting point A directly to input of this op-amp, we can connect it through a resistor like this. This will allow us to add voltage to point C or subtract voltage from point C without affecting point A itself. Now we can add tiny voltage here on point C by pulling it up with another resistor. The higher the resistance of this resistor, the lower the effect of it on op-amp input. You can find proper values for these resistors by trial and error. I found 27 kilo ohm for this one and 2.7 mega ohm for this one. With the same idea, we can use a pull-down resistor here in this way to subtract voltage from positive input. Let's set up this circuit and test it. Yes, it works fine. Look here, in normal situation there is no pulses on output and output is completely inactive. But when I decrease illumination level, output become active for a moment and then it become inactive again. This is just what I need. The circuit we have built so far can only detect one state. It can be sensitive only to illumination increase or decrease, not both of them. But there is no problem. We can use two separate op-amps to detect both states and then combine result of two op-amps. At this time, I'm gonna combine these two diagrams. Look here, this diagram can detect either illumination increase or decrease. This LED indicates illumination increase and this one indicates illumination decrease. Here we add a tiny voltage to this negative input and here we subtract the tiny voltage from positive input. Let's set it up and test it. This LED indicates illumination decrease. Look here. But this one indicates illumination increase. Decrease, increase, decrease, increase, decrease, increase. It is amazing. It works just fine. I can play with it whole day. Look here. Yes. Now the final step is to combine output of two op-amps and connect them to buzzer. As you already know, current drawn by the buzzer can affect output of op-amp. Because of that, we cannot connect the buzzer directly to op-amp's output. It is recommended to use a transistor as a switch to turn the buzzer on or off. On the other hand, we can use resistors to combine output of op-amps. This is how op-amp's output connected together and how buzzer is connected to them. Let's set it up and test it. This is amazing. Look how fine it works. I can play with this whole day. You saw what we got. It is wonderful to fully understand what is going on inside a circuit. This is beauty of analog electronics. I will make more videos of this type. Wait for them. As my last point, I have to say that you can replace LDR with an IR receiver. This is an IR receiver, so-called photodiode. If you do this, your motion detector will be sensitive to IR and will work in dark places. So, I hope you enjoyed this video and learned something new. Thanks for watching. If you like this video, make sure to subscribe for more.